Okay, today's going to be a little bit intense because I try and keep these to about 30 minutes, which for a survey course lets us dive into just enough detail in a particular topic, typically to be, you know, kind of interesting, get a feel for it, and that's the point. Uh, but we're a little ambitious today insofar as we are going to try and cover the fundamental math concepts in engineering in 30 minutes. At least enough to give you an idea of what the underlying math principles are, how the tools are used, how they relate to across all the other domains of engineering, the different fields or subfields, and in particular to give you sort of a scaffolding or a ladder from our target audience, roughly, which is like a second or third semester undergrad engineering student, to understand like what sort of math you should know about, what sort of concepts you should be familiar with to be able to apply them in different fields of engineering. But also, and this is sort of the more interesting part for me, is enough to identify and appreciate and really enjoy some of the concepts that unify all different fields of engineering. Because especially when you look at system engineering and controls engineering, this is near and dear to my heart because I'm like a modeling and simulation person primarily. Ways that you can, it's like a force multiplier, right? You can learn the technique here and it can just explode across all sorts of interesting problems. So without further ado, it's a very ambitious agenda today. I will not at all be surprised if we go a little over 30 minutes because we got a lot to cover. Um, that also having been said, you know, it's been a few years since I went through this rigorously in an academic setting. I've tried to brush up and stretch my brain a little bit. It turns out there were a lot of like, oh, I hadn't memorized all the Laplacian transforms, things like that. But I also have noticed that this camera is constantly trying to auto adjust brightness, and that's really annoying. When I go back and watch these things, and it's constantly like fade in, fade out, fade in, fade out. Um, that's a pain. I thought I had disabled all of those settings, but what you can do, I can see it's still happening. So somewhere in the camera configurations, hope you forgive me. All right, so we're going to focus. There's a lot of math that engineers can benefit from knowing. Um, there's some topics that we're not going to cover at all today. Things like simultaneous equations for the most part, probability and statistics, right? Like error and process noise modeling and filtering, and like lots of really interesting, very powerful, cool techniques. Instead, I wanted to focus on three areas that I thought were sort of core to the fundamentals. Um, so we're going to look at key concepts from calculus. We're going to look at key concepts from differential equations, of course. That's like bread and butter of engineering is diff EQs. And then key concepts from linear algebra. So basically those three areas, and we're going to start with calculus. So calculus, everybody's favorite. I also noticed this lost my pen settings, so it's just wasting. Horrible abuse of feeling here. The pen's still showing up gigantic. All right, so let's take a step back for a moment and think about like, okay, what is calculus, right? So calculus is basically what happens when you take infinitely large numbers of infinitely small things, right? As that limit approaches infinity in both directions, you can do interesting studies and characterizations of rates of change, for example, and that's where derivatives come from. Or you can sum up areas to approximate universal functions, right? And you can move back and forth, and you can combine all these tools and come up with fun solutions for how you transform across those fields. But core to this idea is specifically rates of change and being able to characterize systems across combinations of different degrees of rates of change, right? Like across that integral derivative, boom, 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 discrete spectrum. So let's consider for a moment one of the most important sort of core initial concepts in engineering, right? Which goes all the way back to Newton's second law, uh, which this is traditionally, right, written like this. We're going to take a somewhat more nuanced view here and keeping in mind that forces are vectors, of course. We're going to say the sum of the forces. We're going to add up all of those forces so we can comprise our force model of discrete number of forces that we characterize and define in different ways is equal to the mass of an entity times the second derivative of the displacement. So this combines, this is obviously a very key concept, but it combines a couple of interesting variations on the traditional, F equals ma. First off, we're spatial, right? These are vectors. And second off, we're not specifically talking about acceleration, we're talking about second derivative of state. And state in this case, sneak peek, spoiler alert, state in this case is displacement. So this is the great place to start because it lets us talk about what we might call equations of motion, right? So in a very traditional example of engineering systems, you may have some sort of, spring and a damper and a mass, right? So the question is, you have some sort of displacement of this mass, and this is the state you're trying to characterize. So typically there is a state or a signal or a variable that you are trying to characterize using a model of the system dynamics. And you're trying to get to an expression that defines that state or signal as a function of time, right? That's always what we're trying to go for, is a function of time. We're going to solve for the function of time and then adjust those analytical relationships to obtain a desired behavior, right? That's the core engineering. So we can use things that we know about this system, some sort of damping coefficient, spring coefficient, mass, to start constructing a model of what the dynamics of the system are like. So in this case, we can say, let's see, some forces. So M, we'll use dot notation here, and we're in a one-dimensional system, so we'll ignore the vectors for a moment, right? So given some displacement of let's say from equilibrium, right, of this mass, let's use 0 going up. Like if it's positive, then the damper will be resisting the velocity and the spring will be attempting to restore from the displacement, right? So those forces are actually going to be negative kx minus cx double dot. Say, and then technically the force of gravity, right? So let's say it's going that way. There's some constant forces at play. And we'll just focus on x for now, even though technically this will be like x minus da da da, right? And there will be sign variations. So we have here an expression of the rate of change. It's beautiful. We'll get into sort of the diffie-q concepts later. But right now, this is sort of, keep in mind, this is like the sort of the characteristic expression, right? Other ways that you might rearrange this is you might try to put like all the state on the right, right? Maybe in decreasing order. But typically, and you'll see why we keep the highest order of derivative on the left-hand side and express everything else on the right-hand side, because that helps us formulate the expressions that we'll see later on to construct characteristics equations to do the transforms we want. So this is, let's make it even simpler here and remove our damper and just say, right, we have x. So the acceleration is minus k over mx, and we'll just pretend, ignore gravity for a moment. We're in a vacuum, yay. Sure, that's not on the bottom. I also noticed this laptop screen wiggles. I'm trying to write it. I'm trying to get better about holding that. I hope you'll forgive me. So this is a good example of an equation of motion, right? It expresses the rate of change of some state with respect to some function of that state. And that is a core concept, right? That is the elementary starting point. Maybe you have some sort of point mass or, spherical model or, free body model or have you. You're putting together different forces acting upon the system in such a way where you can express them as a function of the state and the means by which that state changes over time. That will be true for practically everything in engineering. That sort of generalized version of that concept. So this is technically a second order system, right? And it's second order because we have the state and the second derivative of the state. And there are interesting conclusions you can reach when you start combining those things, of course. But for now, just know that we can, if we insert our damper back here, we can get in, we can get back to, we can have the first and the second derivative of the state, etc. Right? So we can build these things up. It's still technically second order, but it's a different kind of system effect. In particular, one of the key concepts here with respect to engineering dynamics is this idea of damping, because this is energy loss, right? This is how energy is actually bled from the system. So if you didn't have that term, the oscillation would go on forever, right? There would be no resistance, there would be no friction, etc. So when you see a second order system without a first order derivative, you just know, oh, there's no energy loss, right? So there's some sort of restorative force, there's acceleration, typically there's some sort of restorative force or resistance, etc. For losing energy, different conclusions you can come to from different parts of the order of the equation of motion. But that's just linear kinematics, right? That is, sometimes we'll call it mechanical displacement as a domain of mechanics, or as a domain of engineering system characterization. Engineers, of course, deal with many, many other kinds of things. So here's another classic example, right? Here is a circuit. There is some voltage applied across that circuit. There is, let's say, a resistor with some resistance R. There is, let's say, an inductor, something like that, and of course, C, right? So classic RLC, right? So let's take the same sort of approach, and of course, we'll see a lot of this, similar conclusions fall out of this. So we're going to use a tool here, which is basically this idea that voltage is what we call a cross variable. So that if you have a serial sequence of elements, the voltage drop across all of those, the sum of the voltage drop across each one. So in this case, we know the delta voltage change across the resistor is Ri. Voltage change across the inductor is Li dot. The voltage change across the capacitor is 1 over C, some integral of I. I in this case is current. Current is, constant unit of or rate of movement of charge. Sometimes you'll see the state here expressed as the actual units of charge. That doesn't express movement, of course. So the rate of change or flow, right? The flow of the charges is current, and that's typically a more useful way to operate. But let's construct a way to characterize this system. So we know the sum of the voltages is equal to the drop in voltage across all the elements, right? And then let's take, you'll notice, of course, here we don't have, I is not like the first order state, right? I is like the intermediate state. So we could take a derivative of this and say V dot is R I dot plus L I double dot plus 1 over C I. And now we have something that's, okay, well, we can rearrange that. We want second derivative of state in this case. Move it over left, everything on right. V in 1 over R plus L over, or excuse me, minus L over R I dot minus L over, wait a second, did I mess this up? I messed this up. This is the double dot. Ah. Wow. Yeah, doing a great job here. I was worried about like doing live math. If there's one thing worse than live coding, it's live math, right? So, Try to ignore this. Let's rewrite this. I knew the L was on the bottom. Okay, so I double dot equals V in over L minus R over Li dot minus 1 over LCI. Okay, there we go. That's a little bit better. So obviously this is some similar form, right? This is the second derivative of our state, what we're treating as state in this case. In this case, we have some constant. We have some energy loss through the inductor, some capacitance. That's a function of the capacitance and linear inductor, divided it all through. So we have some. This is not motion though. This is not an equation of motion. This is a generalized form of the equation of motion, which is called equation of state. Equation of state is basically the same thing. It's an expression of some state, the rate at which it changes over time, as a function of that state itself. So a lot of these, you'll see very, very strong analogies for those concepts across all sorts of different fields of engineering. So let's take, so we saw what? Nope. Oh God. Okay. So we saw in linear kinematics, we had force and displacement, and we had some sort of mass expression, and let's see, first order was, let's see that second order. First order was spring constants, second order energy loss, damping, and mass over 1 over m, right? In electronics, we have current and voltage, and then we have some, let's see, resistance, we have capacitance, and we have inductance. So in hydraulics, for example, we have flow rate or flux and pressure, changes in pressure over unit elements, and we have different ways of characterizing functions in a hydraulic, circular hydraulic elements that result in there's loss, right? There's energy loss of fluid slows down from surface effects as it's moving through a pipe. I can't remember what the term we use for that is. There's ways to store that energy in sump, for example. There's ways that energy can be used and bled off by doing work or with pumps, etc. Same thing in pneumatics. You can imagine pneumatics being practically identical. Compressibility becomes a factor, but I will ignore that for now. Thermal also has strong analogies here as energy is moving through a system, energy and heat. Rotational dynamics, we still have momentum and angular displacement, and torques. That's my really crappy attempt at. Okay, so in all of these situations, we have systems that we can construct elements from using invariance and knowledge for the relationships across what we call across and through variables with respect to how those elements influence the rate of change of those variables. So we can define a state for the system, and we can try and characterize it, the rate at which it changes as a function of the other elements in the system, right? We can use all of our fancy calculus tools to try and characterize that. Very, very powerful concepts from calculus. So now we're going to get into diffie-Q. Yeah, baby. So what we were in the process of building with those relationships were differential equations. We had the rates of change expressed as a function of the things that were changing, right? So that's differential equations 101. We had rates as a function of the state. So we have some characterization going back to vectorized form where there is a rate of change of the state that is a function of the state itself. This is a differential equation. But in very rare cases, can we just like solve those things outright, right? We need a way, particularly since these can be very complex systems. They can be comprised of a number of elements combined in different ways, like your traditional calculus tricks of substitution and maybe integration by parts, like to come up. Remember, what we're always trying to get at is this: some expression of the state as a function of time. That is a solution, right? That is what we're trying to get to. So how do we go from this, where we have a differential equation, to this, a solution for the system, a definition of how that changes over time? Well, it's a lot like integration, but we need a special set of transforms to be able to handle this. One sort of interesting phenomenon or thing that you'll notice in engineering problems, and this is true across a lot of interesting engineering problems, is the way that you view, like the perspective you have of a problem, the way that you define it with respect to some basis, will be very difficult in some ways and very not difficult in others. So it's almost like a pathfinding exercise where you're going through the woods. Well, you can't get their way. You might go around, and then you might be able to find your way this way, and then you might be able to get over there, right? Trying to find your way as a series of transforms through these different perspectives, different bases in which to express the problem is actually an incredibly powerful and incredibly common technique. Let me give you one example that is, of course, near and dear to my heart, which is orbital mechanics, right? So we have Gm1 m2 over r squared. This is the force of gravity, so what is the acceleration, right? So in restricted, excuse me, boop, F, R double dot. Let's vectorize that, so R dot R, right? That's the same thing as the magnitude squared. So in a restricted two-body problem, as we say, this is just replaced by some gravitational parameter. And of course, the mass of the object itself divides out. And effectively, what we have is this. This is not a straightforward problem. Like all of your typical calculus tools will fail you here. This is not linear. It's not at all straightforward. So instead, what we do is we try and we observe this system and try to characterize it in terms of invariance. So trying to solve this in Cartesian space outright with functions of position and time or position and velocity is practically impossible. This is not like the three-body problem. This is just restricted two-body, but instead it becomes much easier when we observe certain invariants of the system. So this was Kepler's observation, right, which is first off, those things are conic sections. They're also sweeping out constant area over time. So there are certain things that are conserved, but there's certain things that are invariant. There's no change in angular momentum because there's no torque applied to the object if it's just a central body, right? All these things feed into a way to characterize the system in terms of invariance. So when you look at an orbit, you'll characterize it. This is in terms of like geometric properties of the ellipse, same major axis and eccentricity, the orientation of that ellipse, inclination of the plane, and the rotation of the plane about the z-axis with respect to some reference, the rotation within that plane of the eccentricity, and then the angular offset. Let's use trigonometry here, within that plane from some reference point, which is typically periapsis, right? So as it turns out, if you characterize it this way, for restricted two-body problem, all of these things are constant except this guy, right? So now you have an expression of this problem where you can say, well, this really crazy nonlinear differential equation, if I reframe it, if I transform it into a different basis, into a different space, suddenly this incredibly difficult problem becomes much easier. And while there's still some transcendental functions involved when you look at the angular transforms, the way you have to project them for different angular space, it becomes actually feasible. So that in particular is just like a great example of the power of transforms in different bases, right? So in a generic sense, we don't always have like orbital elements for our problem or something like that. But with respect to our differential equations, we have a very powerful tool called Laplace transforms. Laplace transforms let us linearize the concept of rates of change. So if you're not familiar with Laplace transforms, basically you think of the s, multiplying by s as a derivative, dividing by s is an integral. So we can have some expression in time that says the second derivative of x is equal to ax dot plus bx plus c. And if we express this relationship instead within a Laplacian space, this turns into a much simpler problem. Second derivative of s squared, s ax plus bx plus c, right? And so now we can c equals s squared plus as plus b, right? X. Boom, boom. That's going to be minus, but they're just constants. Who cares? So, and then once we have Laplacian transform of the space, this is this, right? We can't go directly to here, but if we go over to here, within the space we can refactor or reformulate in terms of x. So you can imagine dividing both sides by that, by this expression. Now you have some x, right? And then you can do an inverse transform to transform it back into the time domain, and now you have an expression, using known transforms. You have an expression for x as a function of time. That is always the end goal, right? So for differential equations, then, when we construct them from the known system dynamics that we saw when we were looking at sort of key calculus concepts, that is typically our approach. We're going to refactor them in terms of Laplacian variables and try and reconfigure them into some form where we can apply inverse Laplace transforms. What that ends up meaning is it's very much worth memorizing your Laplace inverse Laplace transforms in particular. So let's do, can we do a different color? Let's do a different color. Let's do a quick summary. So I would break Laplace transforms into 3 parts in terms of sort of the most important ones you need to memorize. And we're going to do this first just by looking at the identities. So within the time domain, if we have some sort of unit impulse at time t, wow, that's going to be really big. Some unit impulse at time t is going to transform into just 1 in the Laplace domain. But we're also going to be able to take advantage of the linearity within this space. So it becomes, if you multiply, if it's not 1, if it's a constant, like, it's just going to be a constant times that, right, across the linearity of the transform. Some unit step, you can imagine. And that's basically the integral of an impulse, right? So in the Laplacian domain, integrals just dividing by s. Like I said, these are kind of identities. And then we can say like t u of t, which is going to be like, if that's the first order, and then we integrate to get this, then we can integrate that again and get a ramp, right? That's what we're, so that's that tut function here. So that's going to be 1 over s squared. So those are what I would consider like the identities. There are some modestly useful exponential forms. So that's an alpha, believe it or not. In Laplacian space, any 1 over s plus alpha is an exponential decay towards some asymptotic value. If we have 1 over s plus alpha squared, that will transform back into, I'm trying to avoid derivations, by the way, in this series of talks, just because time and complexity, and then how much I'd shoot myself in the own foot. But suffice it to say, there are derivations for some of these that are a little bit less intuitive. But really what I would consider, like, if you memorize any of these, because how often do you see a system that has a perfect response like that, right? Even combinations of these aren't going to be particularly interesting. To a degree, there's ways we can characterize exponential, like, okay, great. But the 2 that you really should memorize, 1 or 2, First off are alpha cosine beta t. If I can remember which one this is. S plus alpha squared beta squared. Did I get that right? Yes. I obviously I don't trust myself for a lot of this. And then sine of beta t is the inverse transform for beta s plus alpha squared plus beta squared. So when you have some sort of equation of state that you can refactor as that function of rates of change, what you'll typically get is some sort of form that you can refactor into like a canonical expression like that, right? And then you can say, well, in this case, the alpha ends up being, expressed as some function of like 1 over LC. I might be wrong, don't quote me on that. We can actually work it out if we want to. Therefore, beta will be, right, R minus over LC, blah, 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 blah. Don't quote me on that. So you can come up with ways to express alpha and beta and plug those into the expression in the time domain. But most importantly, as you may recognize, we can construct very complicated signals as combinations of these things, right? So not only can we apply the tools of linearity, but we can say, well, when we have very complex expressions of many terms here, we can express the time domain as some sum of some sum of these terms, right? Much like we would do with a Fourier transform. So we're then able to characterize the system in terms of like what the decay rate is, and what the frequency of the oscillation is, right? And that lets us characterize things like the settling time for a particular response, or the natural frequency, understanding how energy is moving through the system, which lets us predict a lot of very useful things about the dynamics of the system itself. So we can use those invariants to construct these transforms that let us extract, after a series of linear transformations and inverse transforms, back into what we're always going for, which is this, right? That is the solution that we want. Yeah, it's a lot, isn't it? So this is, as you can probably tell, a second order system here. Well, what if we have 5th order or 10th order, etc.? As it turns out, through decomposition, most systems, especially linear time invariant systems that you'll characterize, no matter how complex they are, will be decomposable into some sum of different terms expressed like this. So that lets us apply a lot of interesting concepts about, like, if you have one term that has a very fast response, and another time that has a very slow response, by comparing these alpha values, for example, you're able to predict, like, well, this term is going to dominate the response of the system because it takes much longer than the other one. This term has a much higher frequency than all of those other terms. So even for a 10th order system, there's one particular dynamic in the transform and then constructing that as a function of the properties of the system. You can say, well, it's going to have this frequency, and that's going to be much higher, and you need to worry about right? So that's too fast for the airplane's going to turn too slow, autopilot's going to induce an oscillation or something like that. Being able to characterize the system even for multiple orders of terms as decompositions of these second order systems is an incredibly powerful tool. And we won't go into controls today. We'll have a separate specific focus on like poles and controls, and we'll touch a little bit on feedback. But suffice to say, those concepts of decomposition of these terms and the dynamics response and the properties of the dynamic response for each individual terms and how they contribute to the overall response of the system from that original differential equation becomes an incredibly powerful tool for engineers. So we have, say, should we go into an example? How much time do we have? We've probably been going on for a while. It's a great topic, but man, we could go on forever. I know there's a clock around here somewhere. Here we go. Oh my God, we're at 35 minutes already. Yeah, this is the problem. And we haven't even touched on concepts from linear algebra yet. So we'll dive into those. God, I don't want to not do an example though. Okay, let's go back to our original RLC, right? This is going to be the sloppiest RLC circuit you will ever see. So we had some I'm going to mess this up because I'm trying to do it so fast. You know what? I might just pull out the example from the worksheet I was doing before for reference. Okay, let's consider instead, because I already had a solution for this, this Matheson damper spring situation, right? This is classical to the point of almost being like degenerate solution, but you know, we'll take it. So in this case, what we find is we apply, so we have some sort of, if we, let's actually even, should we do it even more simpler than that? No, okay. Let's actually show you the example. So ms x squared, right, acceleration, mass acceleration, gravity, cs x minus k x. Okay, so rearrange, this ends up being g over s squared plus cs plus k. We want typically this first term just to be s squared, so we would pull m out of top and the bottom. Fortunately, that ends up simplifying things quite a bit. C over m. A lot of these values that you'll see end up being like ratios between different properties of the system. So now we can use one of the transforms we had, right, for, and back out expressions for, let's see, we know alpha is going to be, s plus alpha squared plus beta squared over, let's see, beta, right? So this is our general form. We're going to pull minus g out because we're trying to go trying to use linearity. And we can, so alpha in this case, we can use this fact, s squared plus 2s alpha plus alpha squared plus beta squared. Map that to this form, right, and conclude that these are the first order terms, so we know, and this is the second order term, so 2 alpha equals c over m, alpha equals c over 2m, right, and then beta, as just as a spoiler alert, is, this is the one I was trying to remember earlier, c squared over 4m. So given this knowledge, right, these are the key insights into the system. If we go back into the time domain, we can say, well, for that mass spring system and mass spring damper, we can construct the expression for x of t, which in this case is minus g. Keep in mind we pulled that out for linearity, right? K over m c squared 4m. That's the linearity term. C t over 2m sine root km minus c squared 4m t, right? So now we can look at this form and we can observe there is some characteristic property of the exponential. There is some characteristic frequency of the response, and we can describe the system dynamics. And eventually, of course, in designing systems as engineers, we'll be able to back that out and reverse the process and say, well, our requirements state that the settling time for this condition be no more than such and such. The frequency response be less than da da da. And then we'll be able to come up with the coefficients for these variables and choose like what the spring coefficient needs to be, and or for a circuit, like what what resistance is needed for that element, right? So in constructing x of t, if you go back to sort of the fundamental models of systems engineering talk that we did, what we're doing here is we have some knowledge of system dynamics that we are attempting to solve for an expression of that over time. There will be some parameters in that expression over time, and there will be some characteristics of the system that we can derive from that expression, and given requirements or constraints that we impose upon that system, perhaps for transfer between two states, for example, we can say, well, okay, now we're going to design the system such that it has these values in order to realize these requirements, right? So, oh God, we're like 40 some minutes. Yeah, 41 minutes and counting. Okay, linear algebra, I promised. So, I did linear algebra last because some of the concepts here not only end up being very powerful, but also end up being very complicated. So speaking of process and systems models from one of our earlier talks, let's go back to this guy, right? Where we have some plant that we observe with some sensors. There's some controller decision that's made that actuates and affects some state or input into the system, right? When we looked at that, we observed, with that model, we observed that we could describe the dynamics of the system for a linear time invariant system, of course. There's some observable output in linear algebraic terms, right? So this is sort of the canonical state space representation of what we call an LTI system. Insofar as it's linear, so these are matrices, right? This is a linear combination of systems, and it's time invariant. Those system dynamics are constant. So you can imagine how we can now apply our Laplacian rules to say, well, there's some S equals AX plus BU, and then we could plug that expression into y, or simply observe here that we can back out the inverse. So S, I, right, and that would go over the left, and then we'd multiply with the inverse B, U. So if you've done a lot of linear algebra, you know that numerically or analytically, this is crazy. There's a lot that can go wrong here depending on A. So out of all four of these matrices, A is by far the most important because it defines the system dynamics, the change of the state with respect to the state, right? Maybe there's other inputs like noise, maybe you're actuating some input to the system, but like the properties of this matrix, when it comes to like what the determinant is and what the eigenvalues and eigenvectors are, end up characterizing the dynamics of the system. And there's many interesting observations we can make. So the first one you might say, well, this is only first order, right? So there's a fun trick here that's worth keeping in mind, which is this is an unconstrained number of dimensions here. So if we have if our state is a three-dimensional position, for example, x equals rx, ry, rz, then x dot would only be the velocity, right? Instead, to capture the dynamics of the system, because as we observed when we're looking at the differential equations, everything's going to be comprised in our solutions of like combinations of second order systems, effectively, when we eventually back out the transforms. What we can say is, well, the state is not necessarily the first order, it's the first order and the second order of our state. So if we can reconstruct this as follows. We can say the state is Rx, Ry, Rz, Vx Vy, Vz. And then in A, we can capture that, the first part as an identity, right? So if x dot equals Ax, we know that x dot of V is Ax. So that's going to be Vx, Vy, Vz, Ax, Ay, Az. So if x dot equals A times x, we know like these are going to be zeros. This is going to be 1, 1, 1, like the 3 identity, right? And then you're going to have really interesting system dynamics here, and to a degree here, where you say, okay, well, this is the actual acceleration, right? So that's where you pull out the second order derivatives. The structure of this matrix we can characterize and constrain in interesting ways by virtue of sort of this shape that's inherent to the second order dynamics. And you can imagine how we could extend this to many, many more variables as well. Your state doesn't have to be 3 variables. It could be 10, it could be 20, depending on how complicated your system is. But we can apply all those tools of linear algebra to this system to characterize the different dynamics. So, so that's how we'd get like nth order system dynamics, and how it's related to sort of the linear algebra properties of our LTI matrices. But we can take it a step further as well, because not only, did I miss some here? Yep. I need to get better at erasing with Skeletor here. Okay, so there are algebraic properties of that system in particular, like is this invertible, right? If that's not invertible, that tells you interesting things about like how valid your assumptions of this system and the linearity of its dynamics are. So I mentioned the determinant of this expression, of this matrix. It will tell you interesting things as well about the stability of the system. You can back out like the characteristic equation from that determinant. That characteristic equation will probably be something like, like this. And then you can look at, the roots of those polynomials and observe based on what, in this case, A is B and B is C, minus 4B over 2. So this ends up being incredibly important, right? With respect to that determinant, is what is the nature of A squared versus B, or 4B in this case. Is it greater? Is it lesser? Is that, so are these roots going to be complex? Are they going to be imaginary? Are they going to be real? And you can immediately reach a number of conclusions about the dynamics of the system based off of the determinant of that matrix and the roots that it gives you based off of where those roots are. So complex roots will give you certain ways to say, okay, this has these dynamics, etc. Real roots will let you know, like, for example, okay, well, there's no oscillation to this response, or maybe it's an exponential increase and it's an unstable system. And now gives you very powerful ways, as you'll see when we get to controls, to be able to characterize how those roots and how the system response changes when you're able to move those around with tools like linear feedback. In particular, like characterizing the stability of the system, being able to take it from an unstable domain into a stable domain, where you have like positive roots that result in an exponential increase in system state versus negative roots that result in a stable. So being able to move those roots around from that characteristic equation to the determinant is like the core of engineering and controls. All right. So that's a little bit of a sneak peek. I'll just say, make one more observation, which is, wow, we're going through so much. So what do we have? Psi minus A inverse. Oh God, I'm going to mess this up so bad because I'm just trying to write it out right instead of derive. C plus D U B. Yeah, okay. What did I want to say here? So if you want to If you go back to sort of our differential equation expression, what you had when you had an expression here, right? If you notice that expression was like 1 over s squared plus a s plus b, uh, was an expression, especially if you kept constant terms from like the voltage, right? Like there was some input into the system that ended up being over here, and there was some function that we were wanting to solve for. That signal, what you can observe about the system is like, so keeping in mind this is a linear expression, right? Is sometimes called a transfer function, or h over s, and this is the output of the system over the input. So what we're often trying to solve for is a characterization of the system that lets us take h over s and multiply it by some input signal to be able to predict what the output signal will be. Right? So if we have certain expressions for u, t, we have an input signal here. So if we can say that we can move this over to the right-hand side like this, we have some linear algebraic expression for, and I'm pretty sure I have this wrong on the right-hand side, so please forgive me. See, that's the expression for x, c plus d, u, c, f. I have this wrong. Given some desired output, we can try and solve for the input. And again, this gets to sort of the harder controls, right? We can try and solve for the input. And in particular, with these dynamics, we can try and come up with an expression for some cost function of the state or input. And then minimize that with, let's say this is Q, right? Minimize that with Q, C, transform Q's. And this gets to some very powerful techniques so this ends up giving us an algebraic Riccati equation for which we can come up with known solutions if it's simple enough that we can guarantee certain minimization or optimization of these system dynamics. So what those dynamics are end up being very interesting and tell you a lot about what the optimal solutions will be as well, especially when you're looking at like problems in optimal control. So that's sort of a brief sneak peek into LQRs or linear quadratic regulators, as well as if you have some form of feedback, right, where your input into the system is kx. You can start dropping this in and observing like, okay, well, the system dynamics, if this is replaced by kx, become, they go from being this to being this. And then, so how can we solve for k such that we minimize this function, right? So now we get into optimal control, which can be very, very exciting and very fun. But we are almost an hour. Like, holy cow, we did not do 30 minutes of math. But okay, so how should we sort of try and summarize this if we can? So key concepts from, let's go calculus first. Key concepts from calculus were this idea of equations of state. Equations of motion being equations of state for like linear dynamics, right? We saw ways that we could characterize expressions for equations of state across all sorts of analogous systems. So we knew we could use all of these powerful mathematical tools, whether we're looking at hydraulics or rotational dynamics or some combination with electronics or what have you, right? We were able to like characterize orders of derivatives and look at how we could construct systems from individual elements to come up with these expressions for the equations of state. From Diffie-Qs, key concepts were, so given the rates as a function of state, we actually have a differential equation, right? And we can transform that into a different space based off of invariance, looking at things that don't change. Using that to characterize spaces where the solutions could be determined in a more straightforward manner. Solutions always being, right, trying to go from this to this. We found very powerful tools in Laplacian transforms and the inverse Laplacian transforms. In particular, if there's one that you memorize, it should probably be this. Right? Memorize this and it will take you a very long way. In fact, at this point, I can probably do it. Oh gosh, which one is this? This sine or cosine? I think it's okay. I spoke too soon. So we could observe the linearity and through combinations of these elements that we'll be able to characterize our system in terms of these two elements of response. We can look at how quickly the system responds and what the frequency of that response is. We can come up with all sorts of conclusions from there based off of dynamics of the system with respect to the way that we would back out expressions for these terms, alpha and beta in particular, as some function of, LQ, or not LQ, in the case of electronics, our resistors and our inductors and our capacitors, etc., depending on what family of engineering we're in, of course. So a damping and frequency response were two particularly interesting. So this characterizes damping, this characterizes frequency response, right? Those are very important dynamics that we want to take into consideration because eventually what we want to get to is some selection of the system parameters that lets us design the system in such a way where we can say we know what the response will be, where we know, jumping to the end, we know we can make guarantees about cost minimization. Anyways, so I'm really going on. And then we had tools from linear algebra that let us characterize state space representation of those system dynamics. And we could extend that to multiple orders of linear time invariant systems. We could observe algebraic properties of those systems, like the determinant characteristic equation of this in particular, right? So we could tie that back to concepts in system stability and dynamics. And then finally, we could relate that to key concept in controls, like cost minimization and feedback, and the way that we could change and adjust the properties of the system and its dynamics by again, selecting specific values to determine what that response that we solve for will be. Whew. We did it. We are like 58 minutes and change. So needless to say, this is not all of the math that you'll need to know as an engineer. But this does cover a very healthy sampling of key concepts. And hopefully it gives you an idea, especially if you haven't gone into some of these topics yet, of what you should try and reach for when you're taking different math classes, what you try and make sure that you cover, and what sort of things you should really try and like grok, right, to really understand at a fundamental level. Like I know exactly how this is going to relate because I know this inverse Laplace transform is going to be this and da 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 da, right? So very key concepts. Next week, so I'll probably do, since I'm alternating now, next episode, probably is some sort of software thing. And the next engineering fundamentals will actually be able to dive into a specific topic in engineering. We covered units and measurements. We covered key concepts, system properties. We covered fundamental, mathematical concepts. And now we can go into statics will be our first topic. So I think I can breathe now. I hope you enjoyed that. Was it good for you too? Have a great time. Hopefully that wasn't too intimidating. Hope it didn't scare everyone away. See you next time.